everybody. What I do for my work is to run applications for customers. Typically, they come to me and they want some website running. I just leave everything up to me or to my company to figure out how many servers we need, application stacks that are running, everything. They typically just want something that actually works. So we operate in data centers. And typically they look something like this. There are some access routers that connect to our backbone. Then there are switches and routers and firewalls perhaps internal to the data center, which eventually routes traffic onto the customer's VLANs. And all of them have IPv4. So if we have one customer that has 150 servers, well, we typically give that customer /24. So /25 would be too little, and so on. And this is what we've been doing for 15 years, and it's been going very well. So a style of doing things that we really like. However, we have some challenges. You probably have noticed that the right NCC ran out of IPv4 address space, which means that we can't continue growing into the foreseeable future, continuing to assign IPv4 addresses to all the servers. There's simply not enough space, and we won't be able to get any more space. Also, our customers, that is some customers, are starting to ask for IPv6, particularly public sector, like the government that have some purchasing guidelines that say you have to ask your vendors for IPv6 and tick the box to say yes, we can do this or not. So we want to introduce IPv6 into the platform. And also this is to come our customer or be a bit ahead of our customers so that we are ready whenever they really start to ask for it. So there are various ways you can approach these two problems. One is a very easy one that many people did during the World IPv6 launch and the World IPv6 Day a couple of years ago. You basically keep everything IPv4 only as before, and way out in front you put a NAT64 device, or a proxy, or a load balancer, or something like this, that terminates the IPv6 connectivity from IPv6 users on the internet, translates it to IPv4, and routes it back into the server. Then you don't have to change anything on the application platform. It's kind of an easy approach to get IPv6 connectivity. So you get exactly that, IPv6 connectivity to your service. That's the good part. The bad part is that NAT64 or a proxy or a load balancer or whatever it is you implement, this has to be a stateful device. It keeps track of every flow that goes to the servers. And that's because the IPv6 address space is so large, so you can't map it into a smaller IPv4 address space without actually doing overloading of the IP addresses. And in order to do that, you need to keep track of state. And keeping track of state is expensive in terms of hardware performance. It's much more difficult to implement a router that can do multiple 10 gigs of stateful NAT traffic than it is to implement a router which does everything in stateless. And typically it also requires that all the traffic belonging to one particular TCP connection or flow needs to pass across the same state translator, NAT64 box, in both directions. If not, you will get a packet that the second translator doesn't know. I don't know anything about this flow, so I don't know how to translate it, so it's going to be discarded. It means that you can't load balance using stuff like equal cost multipath routing or anything like this. And because all of them needs to travel through one translator, you do a failover, you're going to lose all the existing flows. Because the new box you're failing over to doesn't know anything about the existing flows. And you won't see the source address of the IPv6 user, because the NAT64 or the proxy, it will use an IPv4 address when connecting to the server. So the server, which might want to do some geolocation or logging, who was used that actually connected to me right now, it won't see it. It will see some private IPv4 address or some such, which has no relation to the user. And finally, it doesn't help us at all with IPv4 depletion. You still need to use IPv4 for everything. And as such, it only solves one out of two problems, and it's not a complete solution. So, if you go and look on old RFCs from the IETF on how to actually migrate to IPv6, dual stack is the solution. Take everything that has IPv4, you light up IPv6 everywhere where you have IPv4, so that you have dual stack everywhere. And once the rest of the internet is done migrating to IPv6, you can start turning off IPv4 throughout your data center and applications. And that obviously gives you also IPv6 connectivity. So this is a good thing. However, until the entire internet has migrated to IPv6, you can turn off IPv4, which means that you're still dependent on IPv4, and it does not help you with running out of the IPv4. And running two protocol versions at once everywhere is going to increase your complexity with a great amount. Because if you had a firewall rule set for IPv4, now you need to duplicate that firewall rule set for IPv6. You have an application level ACL, you need to duplicate it. If you're monitoring a service over IPv4, you better monitor it over IPv6 as well. And you're increasing the amount of failure scenarios. For instance, you might have a web server talking to the database server using IPv4 and everything is fine. The moment you light up IPv6 on both of them, suddenly that traffic might shift to IPv6. Does that work? Maybe, maybe not. Maybe you suddenly hit some bug that you've never seen before. So dual stack is very hard to do, and it's costly in terms of operational overhead and complexity. So we don't really want dual stack either. We're used to having only one IP stack, and that's simple. And that's simple is good, because simple gives you reliable services. So, said that none of these approaches helps with our IPv4 usage and how to deal with IPv4 depletion. So if we're looking a little bit more into how we're actually using IPv4 in our organization, we have a customer that has, say, 150 server, gets a /24. A customer that has 80 servers gets a /25, at least, maybe more, if we need to plan for growth in the future. So we are using more than one address per server we have in our entire data center. So if I'm counting very quickly, I have about 220 or something like that servers there. I'm using 420 IPv4 addresses in this hypothetical scenario. This is not a very efficient way of using IPv4 addresses, which are scarce and valuable. But if I look even deeper and see what are these addresses being used for, I see that a customer that has a lot of servers might not have so many services that are available from the internet. So you might think of Google by saying that Google has 100,000, hundreds of thousands, or millions of servers. But there's Google.com, YouTube.com, and some others. But I would imagine that the ratio of servers to publicly available services are more than or less than 1,000 to 1. Which means that we are using IPv4 addresses, public IPv4 addresses, for things they could be better used for. Because there is, except for the fact that the web server needs to speak to the database server, there's really no need for the database servers to have a public IPv4 address. So, how can we deal with the problem that we're running out of IPv4? One way to do it is to start using private IPv4 addresses instead of public IPv4 addresses in the data center. And instead put a NAT device, traditional NAT 440 device, out in front, and then set up static mappings for all the web servers, DNS servers, everything that needs to be reachable from the internet. Set up a static mapping for each of them to whatever private IPv4 address they have internally. This will work. Now I use one IPv4 address for each service rather than in excess of one IPv4 address per server. So I'm saving a lot of IPv4 addresses in this way. However, as I mentioned earlier, NAT 4.4, like NAT 6.4, is a stateful technology. And that is not something that we want to put in between our applications and our services and the internet. We can accept that the end users are using NAT in their little home routers out there. We can't do anything about that, but we don't want to put even more NAT in between us and them. Because this causes a potential performance degradation. We lose track of their IP address. We can't do geolocation of them. And it has basically the same disadvantages that I mentioned earlier about NAT 6.4. And NAT 4.4 doesn't help me with IPv6 at all. So, I have some technologies that help me with IPv4 depletion, and I have some technologies that help me make services available over IPv6. So I can combine them. I can use private IPv4 everywhere, no IPv6 except NAT 6.4 and NAT 4.4. That will help me solve both problems. I can also do IPv6 native on all the server lands in combination with NAT 4.4. Now I have dual stack, with all the complexity dual stack gives me out there, and I need to keep track of all the state of all the flows in the NAT box out in front. Or I can do a partial dual stack approach, where I use IPv6 on all the servers and all the applications, and assign smaller IPv4 prefixes that only covers the servers or the service addresses that needs to be publicly reachable. Then I can avoid all forms of NAT. However, I need dual stack in the application stacks, which I don't. So it's kind of pick your poison. Do I choose pest? Do I choose cholera? I can't have my cake and eat it too, it seems, with the traditional ways of approaching these problems. So, what I've been looking for is a better way, a way that actually brings me closer to the end state of having deployed IPv6 without compromising on IPv4 service availability. And the best way I have found is what's called stateless ICMP translation, or SIP for short. It's also been called stateless NAT 6.4 because that's basically what it is. An IBI, which is a bridge between IB and VI, 4.6. And I also wrote a draft, which I should update, about this particular use case in the data center, because SIP in itself is just a generic algorithm to translate between two IP protocols. So, what it is, in a nutshell, is that you take the entire 32 bits of IPv4 address space and you map that one-to-one into a /96 prefix, typical of IPv6, because that leaves you 32 bits to fill out up to 128. So every possible IPv4 address gets a corresponding IPv6 address within your network. And then, in addition, I make some static mappings, very similar to IP or NAT44 destination mappings, to say that this IPv4 address specifically is going to be rewritten to this IPv6 address. And in the data center, or at least in some of my customers' server lands, I only use IPv6, no IPv4 at all. So this is how it looks. IPv6, 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 IPv6. It doesn't really matter how many servers the customer have in this case, because I can put millions in a LAN. My switches can accept it. The only thing that matters for IPv4 consumption is how many services there are. And so IPv6 goes native to the web servers or DNS servers or whatever it is. It doesn't touch on the SIP translation system at all. Whereas IPv4 connectivity comes in from the internet, hits the translator, and progresses into the data center as IPv6. So, I want to show you more in detail how this actually works. So, in this hypothetical example, I have an IPv4-only user with this IPv4 address on the internet somewhere. And in my data center, I have an IPv6-only web server with this IPv6 address. So, and in the center here, I have the SIP translator. So, this user needs to access the web page on this web server. So, what you do first is that you assign a /96 IPv6 prefix out of your own IPv6 address range, typically. For instance, in this case, 64 colon blah 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 /96. And this prefix represents the entire IPv4 address space. Then you take some of the few IPv4 addresses you hopefully still have left, and you say, I'm going to use this prefix as a pool of service addresses that are to be translated into IPv6. In this case, a /24. Could be several prefixes, or it could be a larger prefix, or it could just be single addresses. In any case, you route that /96 to the IPv6 interface of the translator, and you route all the IPv4 service addresses to the IPv4 interface of the translator. And that's just normal routing, OSPF, static, whatever you like. Now, on the translator, you'd set up a static mapping between an address in your service address prefix, in this case, .10 out of 198.50, and you map it to the address of the web server. So you have a one-to-one connection between those two addresses. And in addition, you configure the translator with this /96 prefix as a general fallback for all translations. So that if there is no static mapping, whatever IPv4 address comes in is going to be mapped into this prefix or out of it, depending on which way you're translating. I'm getting there, so it's okay if you don't follow me quite yet. And finally, just add www.whatever into DNS with an IPv4 address of this .10. And of course, you probably want to put in the IPv6 address that is a native, but that's native, so that won't touch this. So, from the internet's point of view, you have a website that has both an IPv6 and an IPv4 address. So it's a dual stack system, so any user can access it. So the user, after he has looked up this address, the address of the host name in DNS, he goes and sends an HTTP request or TCP SYN packet to the .10 address, which is the service address. So it doesn't see that this is a special address that will be translated at all. It will just connect to it like it would a normal IPv4 web server. And since we have a route, and since this address is within the pool routed to the translator, this packet is going to hit this, the SIT gateway. So what the SIT gateway does, and there's the magic. First it looks into the, or it might look into the source field first, and say, okay, the source is 203 something something. Do I have a static mapping for this IPv4 address? No, I don't. So what I'm going to do, I'm just going to prepend those 96 bits in this fallback prefix to form an IPv6 address. Then it goes on and does the same for the destination address. Do I have a static mapping for this address? Yes, I do. So I'm going to rewrite it accordingly. And the rest of the packet is going to be unmodified. So whatever it's in TCP ports, HTTP URLs, it won't look at it at all. It will ignore it outright. And it does some adjustments to the IP header, such as rewriting the version field from 4 to 6, obviously, and rewriting the time to live field to hop limit, stuff like that. It's all in the SIT algorithm. You won't really have to care about it. And one important thing is here is that even though this is just a normal IPv6 packet from the web server's point of view, the entire IPv4 address, the end user, is carried all the way into the web server. So if the web server wants to do geolocation on the end user, or log his IPv4 address, he can do so. He just needs to know that if it's coming from this prefix, it's really an IPv4 client. And I need to strip at least 96 bits to find the IPv4 address. So, in any case, the server's IP stack, and web server software doesn't see this as anything special at all. It's just an IPv6 connection, which it will respond to completely normal as if it was a normal native IPv6 connection. So there's no software that you need to install on the server for this to work. As long as it supports IPv6 at all, this will work. And since the destination of the response packet is within this /96 prefix that represents the IPv4 internet, it gets routed back to this SIT translator, which then proceeds to do exactly the reverse of what it did before. If it looks at the source field, do I have a static mapping for this IPv6 address? Yes, I do. And I'm going to rewrite that address to whatever address is the corresponding IPv4 address. Next, do I have a static mapping for this prefix, this address? No, I don't, but this is the IPv6 translation prefix. So I'm just going to strip off the first 96 bits to form an IPv4 address. Then the packet gets routed back into the IPv4 network and reaches the file. And the circle is complete. And you just, of course, repeat for every following packet in the session. And so neither the server nor the client know that this is happening or needs to have any sort of support for it. So, one of the benefits of this, compared to NAT64, NAT44, is that it's completely stateless. After the translator is done translating a packet, it forgets about it. It doesn't keep track of TCP flows. It doesn't keep track of ports. It doesn't keep track of anything. It behaves mostly like a router, actually. It will, in that it will just forward the packet and translate it and forget about it. Which means that I could have had two translators, one that did the traffic in one direction and another that did it in the other direction, they would not need to share any sort of information in between them, and it would still work just as well. Or I could put 5 or 500, for that matter, translators side by side and use equal cost multi-path routing, for instance, to translate or to load balance between them. So that packet 1 in a flow goes to translator 1, packet 2, translator 2, and so on. Still, it will work just as well as if it was one translator, because it's completely stateless. And when it's completely stateless, and it doesn't keep track of flows, it has the same performance characteristics as an IP router. It means that flows per second is irrelevant, and concurrent connections irrelevant. One thing that matters is bandwidth and packets per second. And it can be easily done in hardware, because it's a very simple and predictable algorithmic translation. And as I said before, the IPv4 address remains known to the server, if it wants to know. It doesn't have to know, it doesn't have to care, but if it wants to find the IPv4 address, it's there in the source address field, in the last 32 bits of the source address field. So all the logging, geolocation, abuse handling that you did with native IPv4, you can still do with this. And it's going to save me a lot of IPv4 addresses, because now I use only one address out of the pool per service. And I don't have to aggregate them. I don't have to set aside a prefix for this customer so that they can grow. Just do 1 and 1 and 1 and 1 and add static mappings sequentially. And that maximizes my usage of IPv4 addresses, of the few that I have left. And since I'm only using IPv6, there's no complexity regarding your staff. Yes, I will have to learn IPv6, and my staff will have to learn IPv6 and deal with IPv6, but they would have to do that anyway if they were going to run dual stack. So it's just going to be a blessing for them to be able to not care about IPv4 as well, and the interactions between the two protocols, and the extra configuration and the extra monitoring and the extra troubleshooting and the extra documentation that a dual stack service would require. And finally, you've actually completed your all your future IPv6 deployment projects. If you do NAT64 in front, eventually you will have to remove the NAT64 and migrate into something else to get native IPv6, and so on and so on. But if you do this from the start, then you're basically done. And when we get to that point in some unforeseeable future where everybody on the internet has IPv6, well, then you can just remove the A record from DNS and shut off the translator if you want. If not, just keep it running on the side, and it will just serve the last remaining IPv4 holdouts. So, and another thing is that since you're routing only certain prefixes in IPv6, /96, and IPv4, the service address pools, it does not have to be in the direct path. It does not have to have a default route pointed to it. It can be on the side, as long as you route those prefixes to the translator. You can place it anywhere in your network, and you can even buy it as a service, I suppose. As long as you have IPv6 connectivity to somebody who has a translation service, you can actually ask them to do the translation for you. So it won't work for every application. It is a form of translation. So if you have an application that does referrals, it won't work, because if the server says connect to this IPv6 address inside the HTTP or FTP request packet, response packet, then the client won't know what to do with that. And since SIT generally will not touch application payload. So for instance, FTP against SIP, for instance, will have problems unless you have some sort of a translator that actually looks into the application protocols and change fields around as well. And I think that for FTP, that's possible to get, but I don't know about every protocol. So this is a good match for this would be, for instance, a DNS server or a web server, or any typical client to server type of application running over TCP, for instance. And in our case, I think 90% of our customers are running web servers or websites. So even if we have to keep the remaining 10% on normal IPv4, we're still going to save a lot of IPv4 addresses by migrating the customers that actually have HTTP servers over to IPv6. So obviously, the whole application stack needs to support IPv6. So, fortunately, Windows, Linux, so on, generally they do that. But you might run across applications that don't support IPv6 at all, in which case this won't work. So it's for certain types of applications it will work. So there are 2 implementations of this that actually work that I'm aware of. You can download Taiga for Linux, which is an open source application that just runs in Linux user space. That works. Might not be something that you want to try to push 100 gigs of traffic through, but a couple of 100 megs, no problem. Then there is the Cisco ASR1K, which have support for SIT. It does not, or might not, support the static mapping feature yet. It was on the roadmap last I heard from Cisco. And so in order to actually use the Cisco ASR1K for this, you will have to also configure addresses on the web servers from within the /96 prefix that corresponds to their external IPv4 address. And you need to route that in the IPv6 network. So it gets a bit more complex, but you can make it work. And I have made it work, and it still saves you the IPv4 addresses, and it still leaves you IPv6 only. So this is my own personal web page, just to demonstrate that it actually works. My browser used IPv4 to connect to my website. And the web server saw this as an IPv6 connection. It responded using this IPv6 address, which is the IPv6 address of the web server. And the client's IP address was from within this /96 prefix, which is allocated out of our IPv6 allocation. And as you can see, the last 96 bits, which you have there, equals, well, the last 32 bits, I'm sorry, of course, the last 32 bits, equals this IPv4 address, which is the address I was sitting on at the time. So it's easy for me to actually see that, yeah, you came in from this IPv6 address, but I know that you really are sitting behind this IPv4 address. So I can do whatever I want to do with that IPv4 address. So that's what I had. So in addition to my own web page, which is obviously not a very large and important website, I'm running our corporate web page through this, through Taiga from Linux. Not a very big traffic website that either, but important enough that I would have been shouted at if something didn't work, and I haven't heard of it. So it actually works. So the major challenge is to get real support in high-end routers or high-end, high-performance implementations to support all the specific knobs, such as the static mapping feature, that is designed to make this a really, really good match for a data center environment. And there are some links to some further reading in case you're interested. So, that's all. Thank you.
Do you guys have any questions?
Hi, this is Mark Johnson from Cisco. Thanks for all this great work, Tori. Have you tried to manipulate our map functionality in order to get some rules to actually do what you need to do here and to make it look like static mapping? I don't know if it worked, but maybe.
I haven't tried, but I think that for map you need also software in the other end of the...
Well, that's how we talk about it. It's map T is effectively using sit. And we should talk about it offline, but there's lots of little knobs there that we can tweak. Might be able to pull it off. Anyway, and another thing I had, and if anybody can do it, I know you can. I'll just give you the idea. He makes our boxes do things we didn't know they could do. And then he finds out the things that it doesn't do, which is that thing up there. And I had the PM on the phone. He's on PTO. He's on vacation. That's why he didn't answer earlier, but he did call me back. And it's interesting the behavior that you explained to me earlier, where you enabled the static mapping mode, which does work, but causes flow tracking to kick in. We actually do the same thing on our NAT44 static mapping, which is known as broken, and so both are being worked on. I didn't get exactly when, but hopefully soon you won't have to do the extra little bit that you talked about there.
Yeah, I hope so. And, the ideal location of this translator, in my opinion, is not in a separate box in your network. It's on one of your core or border or access routers where traffic naturally passes anyway. Because if you put it on a box out there, the traffic is going to shoot out to the side and come back and cause a suboptimal routing. But if it's on your border router where you take transit or here, in a core router where the traffic is typically going anyway, V6 traffic can pass native at the same point. V4 traffic gets translated and continues. That's the optimal location of it, in my opinion.
So an ASR 9K type box?
Perhaps. I mean, it also depends on the size of the shop, I guess. If you're not pushing many gigabits of traffic, then I guess you can do with the Tiger solution. But if you want multiple thingy cores, I wouldn't recommend that. The ASR 1K is probably somewhere in between.
Any other questions? We still got about 5 minutes.
Thank you.
Thank you very much.